My name is Ali Fahmi, as mentioned earlier. I'm a postdoctoral researcher in epidemiology at the University of Manchester. I completed my Ph.D. in computer science under supervision of Dr. William Marsh at Queen Mary University of London in, I think, 2021. And the title of my thesis and the title of this talk is Decision Support for Rheumatoid Arthritis Using Bayesian Networks, Diagnosis, Self-Management, and Personalized Care. The outline of my talk includes the problem description and decision support based on Bayesian networks for diagnosis, dynamic Bayesian networks for self-management, and a recommender system with a Bayesian network model for personalized care. And finally, I'll summarize and explain the future works. So the problem focuses on chronic diseases that are long-lasting and need lifelong care. Rheumatoid arthritis is a chronic disease affecting 1% of the UK population and causing swollen, painful joints. And develop flares or flare-ups occasionally. The Bayesian was a research project to develop Bayesian network-based decision support for managing 3 chronic diseases, including rheumatoid arthritis. And this research was in the framework of the Bayesian project. The Bayesian networks that we developed aim to support diagnosis, management, and personalized care for living with the chronic diseases, and the decision support tools would allow clinicians to monitor patients remotely and involve them in self-management of their disease, enabling clinicians to taper medications to reduce the dosage of medications. And for the modeling of these the decision support, we mainly used experts' knowledge and data. But I will explain that the data that was available to us was, in the first stage, was rather complete, but progressively it was less available and eventually not available at all, which I'll explain the next slides. The Bayesian networks for diagnosis, the first stage of my PhD, was around the problem of diagnosing of chronic diseases. The aim was to show how to build a Bayesian network model for diagnosing rheumatoid arthritis. And the available evidence included experts' knowledge, mainly the data, literature, and clinical guidelines. And the main challenge was knowledge acquisition from experts or other sources. This is the structure of the Bayesian network model for diagnosis that we developed. You can see this diagnosis variable was the target, which was differentiating the rheumatoid arthritis from other inflammatory arthritis. You can see the risk factors on top here, also here, and the comorbidities, relevant comorbidities on this side. And the signs, mainly the tender joints count, swollen joints count, here as the manifestation of the disease, right? And then you can see the inflammation, inflammation marker, I guess, they call it on here, ESR and CRP. So these green ovals represent the observation variables. They may be observed, preferably all of them observed, but some of them can be not observed. So our approach is here knowledge-based, as the name of the model expresses, the knowledge model. We try to bring some information that we try to elicit some information from experts that does not exist in the current clinical practice. For example, these two variables related to females, which can contribute to the female sex hormone fluctuations, can develop the rheumatoid arthritis disease. But these two personal factors for females are missing in current clinical practice in the UK. They don't record the early menopause or pregnancy or postpartum. But we wanted to bring them into account here. So the experts provided them. They were originally taken from the established literature, and the parameters for them were learned from experts. A similar situation was here with these two genes. But for the other variables, we had some sort of data recorded and used for training and testing. Here, we developed another model purely from data. We use the structural expectation maximization algorithm to develop this. You can see these arcs here. There are many of them compared to the other model, the knowledge model. Some of them make clinical sense. Some of them make no sense. The causal meaning is missing at some of them. For example, here you can see the diagnosis variable is connected to the CCP, antibody CCP, and connected to rheumatoid factor, antibody rheumatoid factor, which makes complete sense clinically, but some of them are not. For example, variable ESR is connected to variable biological sex, which we never understood them. We refers to myself and the experts, the rheumatologists that were collaborating with us. We call this model the learned model, and the other one, the knowledge model. You can see the metrics of their performance. Clearly, the knowledge model outperforms, and you can see here the outperformance of the knowledge model. And also the confusion matrices, again, 80% and 69%. In the second stage, we focus on the problem of self-management of chronic diseases. Our aim was to show how to build dynamic Bayesian network models for self-management of rheumatoid arthritis. In two stages. In the beginning, we focused on appointment scheduling advice. And in the second one, which was built on the first stage, the model of the first stage, we focused on medication review. The evidence was a set of data that was not the way we wanted them to be. I'll explain later, and the experts' knowledge, clinical guidelines, and literature. The challenges was the fact that we wanted to provide remote monitoring, and that kind of platform does not exist. So, or may be existing somewhere, but we didn't have access to. And the frequent data that we needed for the dynamic Bayesian network model was not available to us, and I don't know if it exists or not anywhere in the world. And knowledge acquisition again. This is the model for appointment scheduling advice. You can see that variable here represented by this white oval. This is the final outcome of this model. In this area in the middle, you can, which is called the temporal plate, we have got the main structure of the dynamic Bayesian network model. And as you may know, in the dynamic Bayesian network models, we have got time slices. So this temporal plate, the structure in the temporal plate would repeat in each time slice. These arrows with number 1 on them are temporal arrows. They will connect the model from one time slice to the next time slice, basically. Again, you can see here these in the bottom of the structure. These green ovals represent the main serology results, the symptoms and the signs and the symptoms that are relevant for disease activity measurement. The main variable that we wanted to, the main latent variable that we wanted to estimate its probabilities was disease state, and which is now in the clinical practice being measured by a metric called disease activity score 28, DAS 28, which takes into account these CRP or ESR, and tender joints count, swollen joints count, and global health. We brought them here into the model, but our approach is probabilistic. That one, DAS 28, is rather a simple equation, just summation of some things, and quite simpler, and maybe not accurate. We also try to measure the occurrence of flare, and the other two aspects of flares, frequency and duration, and then we aggregate them into a variable called overall flare. In addition, we take into account the disease progression trend. So we want to know whether the person is deteriorating compared to the previous time slice, and whether they are improving or stable. Being stable is what we expect, but we wanted to measure that trend. The same trend was considered for overall flare, and then the two trend variables and the overall disease control lead to the appointment advice. On this model, you can see the unrolled model. We assumed that the time is weekly, based on experts' knowledge, which was originally based on the frequency of medication that patients should take. So imagine we are on week 4 now, and week 3 was just before that, and connected as it's shown here. These observations should be given, or maybe given to the model in week 3, and now in week 4 they should be given, and then the probabilities would be updated for the overall disease control and the other trends. And from them, we would see the probability of the appointment scheduling advice. So this person is on the standard monitoring with a higher probability, so they are able to their disease. Otherwise they needed enhanced monitoring, and they could be appointments being scheduled for them. We try to evaluate that the performance of that model by defining enhanced monitoring being corresponding to the major flare, and the major flare was also taken from the data that was interpolated. As I mentioned, we didn't have the frequent enough data, so we had to interpolate them, make them into something that looked like weekly. And we obtained 82% accuracy. Here on the right-hand side, you can see a case who is in the beginning. You can see here, this is DAS28, the metric that is currently measured. The person is not doing very well in the beginning because the DAS28 is above 5.1, which is a very high disease activity. And at the same time, our model is suggesting enhanced monitoring. It is above this blue line, the threshold. So enhanced monitoring is advised here. And then gradually the patient does well, goes even below the red dashed line. And our model also goes below the blue line until week 28, which the patient starts having a upward disease state, disease activity score 28, and basically a flare happens there in this time, and we also suggest enhanced monitoring, and then eventually the patient does well, goes below the disease activity goes below the line, and our system, our model advises standard monitoring again. Then we built on that model. We added the medications. As you can see here, these are the medications that are added, and also we considered a concept of tolerance, which was given by experts to us. So experts explained that some patients are quite tolerant, some are not. These medications are quite toxic, although they are effective, but they can be quite toxic. Some patients may not be very tolerant, and also there can be adverse events. For example, organ damage, mainly liver and kidneys, or symptomatic side effects such as headache, vomiting, and so on. We also try to capture the trend of adverse medication events and take it into consideration for the final medication review advice. And the rest of the model, the area in the bottom is not almost, it is identical to the model in the first stage. This is again unrolled. Imagine we are in week 5, and based on the observations that are given to the model, the medication review states escalation or same regimen or tapering or medicine change having their probabilities. This patient looks like to be on the same regimen state. We again, with the same interpolated data, we try to evaluate the model. Here you can see the concordance table. The 2 states seem to be doing well, but the other 2 states, namely the tapering and escalation, are not very well. We expected them to be higher. So further evaluation and improvement of the model is needed. The last stage of my PhD was focused on the personalized care for living with chronic diseases. Our aim was to show how to build a recommender system with a Bayesian network model to provide personalized advice for living with rheumatoid arthritis. The evidence was experts' knowledge, mainly, and literature, clinical guidelines, online contents from the NRAS, National Rheumatoid Arthritis Society, and a coded review coded interviews with patients. You can see there is no data here. So we built a Bayesian network model from no data. And that was the main challenge in this stage. Here you can see a flowchart of that of the recommender system. Initially, the data of patients are collected, and then they are fed into a Bayesian network model for quality of life prediction. I don't go through the Bayesian network model, but that Bayesian network model basically estimates 3 components of quality of life, including empowerment, participation, and independence, which are corresponding to physical, social, and psychological aspects of quality of life, respectively. And then a set of advice. The model would give us the probability of which aspects of quality of life should be targeted to be given advice for, and then based on the contents that we found from the NRAS, we took the advice. Then we furthered the advice based on the observations that patients would be giving. For example, the patient would give us that would specify that their sleep quality is not well. Then we would give an additional advice. I'll come back to that. Let me just finish because I think 1 slide or 2 remains. And then the advice is modified eventually based on the person's given observations, and a set of personalized advice is generated. We tried to evaluate it. There was no data, so we just used a set of scenarios to evaluate the performance of the Bayesian network model. So in summary, we built and evaluated Bayesian networks for diagnosis, which can be used in primary care or even secondary care. We built and evaluated dynamic Bayesian network models for self-management, which can be used for remote monitoring of chronic diseases. And we built and evaluated a recommender system with a Bayesian network model for personalized care, which can be added to the remote monitoring of chronic diseases. Thank you so much.